Our last method of numerical integration is Simpsons Rule, and again we're going to derive a formula for an approximation to the integral from a to b of f of x dx. And we start by dividing the interval from a to b into n equal parts, and in this case we always assume n is even. And to find our approximation, we recall that 3 points in the plane determine a unique parabola. And so we start by pairing the first two subintervals from x0 to x1 and x1 to x2. And we get 3 points on the curve above x0, x1 and x2 respectively. And we can draw a unique parabola through those 3 points. And then we move on to the next two subintervals, which we pair. They're the intervals from x2 to x3 and x3 to x4. And again we draw a parabola through the 3 points on the curve above the points x2, x3 and x4. And we continue on in this way until we've exhausted all of the subintervals in our n subinterval. Now our approximation to the integral from a to b of f of x dx, which is the area under the curve in this case, is equal to the sum of the areas of the regions beneath these parabolas and above the x-axis. So we can derive a formula for this area using basic geometry. The area beneath this first parabola above x0, x1 and x2 is equal to delta x over 3 times f of x0 plus 4 times f of x1 plus f of x2. Area beneath the second approximating shape is the area under the parabola sitting above x2, x3 and x4. And its area is delta x over 3 times f of x2 plus 4 times f of x3 plus f of x4. The general formula is that the area beneath the parabola sitting above xi minus 1, xi plus 1 is delta x over 3 times f of xi minus 1 plus 4 times f of xi plus f of xi plus 1. And we estimate our definite integral from a to b of f of x dx by summing the areas beneath these parabolic segments. And this is called Simpsons Rule. And when we sum, we get the following formula. We have delta x over 3 times f of x0 plus 4 times f of x1 plus f of x2 plus f of x2 plus 4 times f of x3 plus f of x4 plus f of x4 plus 4 times f of x5 plus f of x6, etc., etc., etc. The final formula is delta x over 3 times f of x0 plus 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3, etc., etc., plus 4 times f of xn minus 1 plus f of xn. And of course we have the usual formula for delta x, it's b minus a over n, and xi is a plus I times delta x. Actually, Simpsons Rule using 2n subintervals is equal to 1/3 of the trapezoidal approximation for n plus 2/3 of the midpoint approximation for n. So it's a weighted average of the trapezoidal and midpoint approximations for half the number of intervals. Well, let's try this out for our n equals 6, which is certainly even, to approximate the integral from 1 to 4 of 1 over x dx. And of course we've approximated this before using the midpoint rule and the trapezoidal rule. And we've done most of the calculations. Delta x is 1/2 as usual. The xi's are 1, 3 over 2, 2, etc. And f of xi we've calculated before, and it's shown in this table. Filling this into our formula, Simpsons approximation with 6 approximating subintervals is delta x over 3 times f of x0 plus 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3 plus 2 times f of x4 plus 4 times f of x5 plus f of x6. And filling in the details, we get 1.387698413. Now the error in this estimate, the absolute value of the error, is 0.001400405. So that's certainly the best estimate that we've had so far, and most likely the reason for this is drawing parabolas actually catches a little of the curvature on the curve.